All right, great. Thanks for the introduction. My name is Pranav. I'm a PhD student at the University of Michigan. And today I'm going to talk yet another talk about automation at scale. And I'm going to talk a little bit more about how modules might offer a potential lens for us to be able to better understand and manage automation when it runs awry. This is joint work with John, Oded, and Andrea at VMware Research. So this trade-off has been talked about a lot already, but I'll talk about it again. But quick caveat before I begin, the work that I'm going to be presenting was done using Virus, which is a Dafny'-inspired language built on Rust. But it follows the same using of SMT for verification. So both languages face this trade-off that we've been talking about a lot today, right? We want to have maximizing automation. We want to push towards writing as little proof as possible. But at the same time, as we tend to go towards that side, we might be sacrificing fast and stable verification, right? And ultimately, this is predicated on the size of the quantifier search space. The more quantifiers you end up having in your search space, the more you might be able to find for free, but the chance of running into some kind of unhelpful instantiation and falling into some kind of rabbit hole search might end up ending up costing us verification. And we might move towards the other side with a smaller search space, but this is when you might need to manually intervene with some kind of assert that wasn't able to be found automatically. And there's been some talk about different philosophies as to how to manage this trade-off. So one talk, the Dafny'24 talk was an example of this, and there was this recent Daphne blog post as well that kind of says maybe we should aim more towards the fast and stable side by breaking down our steps and having a little bit more physically written down. And I'm here to maybe present a slightly alternate philosophy to this idea, which is maybe we should be pushing towards as much automation as possible, but we need good tools to be able to diagnose when automation is hurting our performance, so we can just kind of rein it in at those points, as opposed to maybe forgoing it overall. So before I talk about what tools currently exist, I'm just going to do a quick recap or introduction to what quantifier instantiation is. So say here, in this case, we have a verification condition of pong of 4, and we start with this initial fact of ping of 1. This, with our two instantiations that are available in our program, will trigger the ping-pong lemma in this case to be able to learn some new ground term of pong of 2, which in turn will let us learn ping of 3, which in turn will let us learn pong of 4, which is our verification condition. And what the quantifier instantiation graph is really capturing is this causality of this search, right? This is a relatively straightforward example. There's not much of a graph here, but in general, this search process is a much more complicated DAG that captures what instantiations are happening and what is causing those instantiations to happen. And so the current tools that kind of work with this quantifier instantiation are pretty good at what we call local fixes, right? So the Axiom profiler has a way to visualize this full quantifier instantiation graph. And it's even pretty good at identifying what we call trigger loops, like the one I showed on the last slide, where ping and pong can potentially go on forever and fall into some rabbit hole of search. Another example is this cost metric, which is a way for you to aggregate across this quantifier instantiation graph and get a ranking of which instantiations are particularly nasty or causing a lot of cascading instantiations. And then we used our usual techniques of fuel and opaque to try and patch these points up. Right? So the current workflow looks something like this. We have some search space that's available to us based on our current definitions. Maybe we add some more definitions, but we added some problematic quantifier that's slowing everything down. We use our tools to be able to identify, okay, this is the one that was causing that, and then we patch that. But at a certain point, maybe the search space itself becomes an issue, right? Once you get to larger and larger scales, you can't just continually introduce new facts into your context without running into search space. And the way we go about managing complexity in standard software engineering practice is to start encapsulating, right? We use logical separation of concerns to be able to split this idea. But the way that modules interact with automation is probably slightly more nuanced than that, right? In that we have a notion of automation leaking through module boundaries. And this can be a good thing, right? So here's a quick example. We have two modules where the data type of the larger one builds on the smaller one. And say we expose some interface in like a standard software engineering paradigm. We expose some lemma and two predicates. And even if module B is only ever using predicate 1 and predicate 2 in an uninterpreted way, in this case we don't necessarily care about their definitions, the latent automation of this for all is still available in the search space of predicate module V. And I would argue that that's probably a good thing, at least in like smaller cases, right? But when we start to run into issues is maybe when we're okay paying this cost at a local scale, but when we start building on top of this, we don't want to necessarily continually pay the cost of lower automation. We might want to be able to put up we don't want to end up paying this cost. And one way we might handle this is to kind of put up a clean interface at module B that kind of prevents us to be able to leak through. So the question that we try to investigate a little bit further here is that, okay, we have this idea of where we have the tooling to be able to put up these kind of module boundaries, but we don't understand where to put them up in a larger code base. We don't have good tools to be able to identify when this automation is leaking in a way we don't understand. So can we use a module-based lens to better understand how automation is scaling on larger code bases? Okay, so that was the motivation. So the rest of this talk is going to be a case study on a relatively large Virus code base for a key value store. It's on the order of around 20,000 lines of code and proof altogether. And it has a pretty rich module hierarchy. So that's why we thought this would be a good candidate to try and identify. Can we pick out the problematic modules in some kind of meaningful way? Okay, so let's talk a little bit about what kind of transformations we did on this base idea of this quantifier instantiation graph that we started with, right? So when we directly just tried to use the quantifier instantiation graph, our proofs had on the order of like 100,000 instantiations, so directly visualizing it proved to be quite untenable. So the first thing we wanted to do was try and improve the visualization of this, this graph in a way that preserves the module information, but is slightly coarser, and we care more so about what modules are causing instantiations in others. So if we go ahead and label all of the instantiations with which modules they belong to, so each shape you can think of as a different module. The first insight is if we're talking about modules at a sibling relation in the graph, and they belong to the same module, if we only care about module granularity, we can go ahead and merge those, right? And we can do the same, I have another example down here. We can go ahead and merge that as well. And now I've introduced some numbers as well, which I'll explain right now. So this 4, all it's basically capturing is how many instantiations lie below this point in the original graph. So the original graph had 4 instantiations that fall below. And this is not dissimilar to what the cost metric is doing. This is just doing it at a slightly more modular granularity, if you will. Okay, so now that we have this idea of like a module granularity quantifier instantiation graph, the next question we can kind of ask is, okay, if we cut off the automation at a particular module boundary, what would that look like in this proof tree? So for example, if I were to cut off the search at the blue square module, then we effectively eliminate 10 instantiations in this toy example, right? So we can come up with this metric of how much of the proof am I cutting off by putting up a boundary at this particular module. And we can do the same thing for each of the 2 examples here. And we'll get like a total histogram of all the modules. And it's worth noting here that this is not a partition of the instantiations. We're not exactly characterizing what caused a particular module or what caused a particular instantiation. It's more so a way to get a ranking of which modules might be good candidates to put up boundaries at. Okay, so let's talk a little bit about running this on our code base. So this is an example of the result we saw for a particular proof inside the code base. And this was a refinement proof in the filter about a filtered BE tree. And so there's some candidates here that you would expect, right? You would expect the module itself that has this proof to show up with particularly high blame. And because it's pretty tightly coupled with the underlying data structure, you'd expect those 2 types to appear pretty high. And the other thing you might expect to see here is modules that represent the standard library, right? This is part of the latent automation of tools like Dafny and Virus. So those are not particularly worth considering a little bit more. The module we decided to investigate a little bit further was this one that we couldn't quite explain. It was a buffer seek module that appeared slightly lower in the hierarchy, and it was causing this ballooning effect, and we didn't really quite understand why. And moreover, when we compared it just to raw instantiations, it actually appears quite low. So it seemed like a good candidate to try and investigate where is this automation running away within this particular module. And the strategy, as many people have talked about before, is that opacify and specify, as we've seen before, right? So we were able to identify which quantifier inside this module was being particularly problematic, which happened to be a predicate definition. And the strategy for doing that was very similar to being able to merge across a specific quantifier as opposed to a module. So not dissimilar to the cost metric once we distilled it down to where the automation was going wrong. And then, yep, we make the definition opaque. And then we took a look at this intermediate stage when the proof is broken. What did the search space look like here? And the instantiations actually cut down to only 33,000. I realized I forgot to point out the number before. In case you forgot, it was around 100,000 instantiations. So like this kind of suggests that just by cutting off this one definition, we were able to, I guess it suggests that this definition is causing a large ballooning of search to happen underneath it, even though maybe there's some Z3 mysticism going on there that we don't fully understand. But somewhere within that triangle of proof that we saw underneath, we had some fact that we cared about that we needed to figure out what it was and expose. And this is the new interface we want to present for the buffer-seek module, right? So we were able to isolate, okay, this is the reason why that proof was going through before. And we were able to expose it as its own independent lemma. So this is the same strategy that we've seen like presented multiple times today already. And after we did this refactor around this opaque definition, we were able to, let's take a look at the results, I guess. So the big win here is that we have a large reduction in the total instantiations that have in this roof. And this translated over to a runtime reduction as well. I think it's like on the order of like 2x. I don't remember the exact numbers. But what's still not quite clear to us, and still warrants further investigation, is why buffer-seek is still appearing particularly high. So maybe this is a tool that you might use when you have something problematic, and now that this is running in some acceptable threshold, we don't necessarily need to. But it's clear that this tool is not telling the full story as of right now. We need further investigation to be able to maybe decipher between what's happening at the module boundary, and maybe the new lemma is, so let me back up one sec. Most of the instantiations that were falling out from the tree after we did this transformation were due to the precondition of that lemma we introduced. So there's perhaps some distinction we can have between what we expose as the boundary, and maybe you can quantify this as not necessarily part of that module's count. So maybe there's further work to be done refining this metric. But that leads to some questions, which is there actually such a metric that can unambiguously identify the difference between like a leaky module and when this automation is failing us? And then popping back one level even above that is, we started with this assumption that leaky modules would be a good way to curtail automation, but perhaps that's not even really what's going on here. Maybe there's a different way different lens you can use to try and view this, this problem that can point out other things. And then one more pop-up, I started with like this philosophical claim that maybe we should be pushing more towards automation and having tools go about it. But I think there's a lot of discussion to be had here, as I personally think that the automation is a good thing, and if we have like the tools to be able to pick out when it's failing us, then we can leverage that automation a lot better. That's all I really had. Thanks for your time. And questions, yeah.
Yeah, maybe it's probably me, but I didn't quite understand the tree you showed with the different modules. Mm-hmm. Some modules occurred multiple times.
Yeah.
So I wasn't really sure. Is that like different usages of different members in the same module, or?
So even instantiations even quantifiers can appear multiple times in that instantiation graph. So each node represents a specific instantiation. So even within like a standard quantifier instantiation graph, you might invoke like the ping pong lemma like 3 different times. So that will appear like 3 different nodes. But yes, sense. This is also aggregating across if there were multiple quantifiers inside the same module, we'd also aggregate across those.
All right, thanks.
Yeah.
A very great talk. You said, if I understood right, that the preconditions were also creating like their own instantiations. Have you tried like making the precondition in an opaque predicate, for instance?
Oh, that's a good idea. I haven't tried that, but that's definitely a good thing to try. Yeah.
I guess that's all. Thank you very much.